So today we're going to talk about Taylor polynomials and some of their applications. So a Taylor polynomial can be used to represent a function to a certain degree of accuracy by using tangent lines. Essentially, if you have a bunch of tangent lines of a function, it will eventually represent the function with infinite accuracy. So if we have a function y equals f of x, then the first degree Taylor polynomial will be equal to f of a plus f prime of a times x minus a. So again, that notation there, t sub 1x is the first degree Taylor polynomial, and a is the value that the Taylor polynomial is centered around. So on a graph, that would be basically the value that you are, the x value that you're basing all of your tangent lines around. So we can expand this definition, and it will become, so the nth Taylor polynomial is f of a plus f prime of a over 1 factorial, rather, times x minus a plus second f double prime, or the second derivative of f at a over 2 factorial x minus a squared plus, and so on. And so then the general formula is f to the nth derivative of a over n factorial x minus a to the nth exponent. A is the value that the Taylor polynomial is centered around, and n is any integer. So some properties of the Taylor polynomial. When the value that the Taylor polynomial is centered around is 0, it becomes a special type of Taylor polynomial called the Maclaurin series. So we can use a sigma notation for the Maclaurin series, which you can see there. Additionally, if we are multiplying two functions, so for example f of x and f of x and g of x, and if f and g have the Taylor polynomials t and t prime, then the Taylor polynomial of the product of f and g is obtained by taking the product of t times t prime and dropping all terms with powers greater than n. So another important concept is linearization. So if y equals f of x is a differentiable function at a, which is any number, then its graph can be approximated by its tangent line on small intervals. So for example, so y minus f of a equals f of a times x minus a. So this is kind of similar to what we saw in the Taylor polynomial. And then y would be equal to f prime of a times x minus a plus f of a. So the linear approximation of f of x at a is f of x is approximately equal to f of a plus f prime of a x minus a. Again, this is known as the linearization of f of x, which is also known as L of x. So procedure for approximations. First, we want to take an equation that represents what we're trying to find. So we'll kind of go over that in the video example. And then we want to take a number a, which is sufficiently close to the given value. So a should be a number that is easily calculable for the function, which again we'll go over. And then finally, you just want to evaluate the approximation using the formula. There are some reasons as to sort of why it works. So additionally, we can do this with derivatives. So if y equals f of x is a differentiable function, by definition, the differential dy equals f prime of x dx, where dx is an independent variable. So then follows through, and we can essentially add the derivative of x to a if needed. So for our examples, we'll go over how to find a third degree Taylor polynomial of that function shown there around a equals 2, and we're going to use linear approximations to evaluate cosine of 1. And then the extra example, we'll try our hand at a Maclaurin series. But for now, we'll just use the Taylor polynomial and the linear approximation. So we want to find the third degree Taylor polynomial, so I'll just say T3x of y equals x to the fourth minus 4x to the third plus 2x squared plus 5x plus 3, centered around 2. So what I'm going to do first is find the first 3 derivatives of this function y. Because we're looking for the third degree Taylor polynomial, we need the first 3 derivatives. So y prime is equal to 4x cubed minus 12x squared plus 4x plus 5. Second derivative is 12x squared minus 24x plus 4. And the third derivative is, 24x minus 24. Okay. So once we find those, we can then put it into our Taylor polynomial equation, our formula for it. So I won't write it out, but I will. I'll just mention it. So we have f at a. So y at 2 would be. Actually, what I'll do as well is I'll just put in the 2 for x here. So this becomes 4 times 8 minus 12 times 4 plus 4 times 2 plus 5, which is equal to -3. And this one, so 12 times 4 minus 24 times 2 plus 4 equals just 4. And then 24 times 2 minus 24 equals 24. And then I should write down as well, so y equals, I'll say y of 2 equals 2 to the fourth minus 4 times 2 third plus 2 squared plus 5 times 2 plus 3. And that is equal to 5. So then, so we'll put this in the formula. So once we found f of a and f prime, f double prime, f triple prime of a, then we can put it in the formula. So we have f at a, which is 5. Sorry, I should say t x equals 5 plus the first derivative at a, which is negative 3, over 1 factorial times x minus a, which is 2, and then plus our second derivative at 2, so 4 over 2 factorial x minus 2 squared, plus our third derivative, 24 over 3 factorial times x minus 2 cubed. So I'm going to leave it like this. You can simplify. You can probably get rid of those factorials. Actually, maybe I'll just get rid of the factorials. And 2 factorial is just 2, so we'll just divide that there. And 3 factorial is 6. All right, so that is our third degree Taylor polynomial for that function. So that was our first question. And then our second problem is using a linear approximation to evaluate cos of 1. So we don't quite know that yet, but what I'm going to do, so I'm going to find an equation that we can use to evaluate this, and this one's pretty simple. We don't need to think too much of it. We can just say f of x is cosine of x and then for the value that we want to choose for a, which is close to 1 but not equal to 1, and one that will work within the context of cosine of x, I'm going to choose pi over 3 because it is approximately equal to 1.031, which is approximately equal to 1, so it's a pretty close estimate. So that means that cosine of 1 is approximately equal to cosine of pi over 3 plus the derivative of cosine of pi over 3 times x minus pi over 3. So, excuse me, this will be equal to cos of pi over 3 is 1/2, and the derivative, so root 3 over 2 times 1 minus pi over 3, because x here would be equal to 1, because that's what we're looking for. A is pi over 3, and this is equal to approximately 0.54004. And just checking that on a calculator, cosine of 1 is 0.5403. So pretty close approximation. Of course, the closer you can make a to x, the better the approximation, but it does work out pretty well. So that's everything for today. Thank you again to Loom and Google Keep, and to my professors who taught me this, and I hope this helped. Thank you for watching.